if I go back to the example and I think to myself, well, R was 6. In this example, there are 3 observations for each of those 6 tube types, so there's a total of 18 observations. So N is 18. That makes degrees of freedom 18 minus 6, or 12. And my S squared then is going to be, well, the denominator will be N minus R, or 12. The numerator will be twice. Well, there's a 25 here, there's a 58.33, there's a 108.33, down to a 25. And so 3 minus 1 is 2. 25 times, 2 times 25 plus 3 minus 1 is 2 times 58.3 plus 2 times 108.33, and so on, down to sample number 6. Has sample size minus 1 being 2 times an S squared value that's 25. That turns out to be 69.44, and that's in units of microamps squared, so that the pooled S is the square root of that 69.44. That's about 8.3, where the units are now the original units of microamps. This number is a single number estimate then of the variability in current requirement associated with any fixed tube type. So that's what sigma is. Sigma intends to measure the variability in response, that is current requirement, for any fixed set of process conditions. To turn this single number estimate into confidence limits, I'll take this 8.33, so let's talk about 95% confidence limits. (95% confidence limits for sigma are then going to be this 8.3 times the square root of degrees of freedom over chi-square value. Degrees of freedom are 12. That's the number of observations minus number of groups, N minus R. And if I pull out the upper 2.5% point of chi-square 12, chi-square 12 distribution, I get 23.337. And if I take 8.3 and I multiply by the square root of 12 over a lower chi-square value, that's 4.404. That's the lower 2.5% point of the chi-square 12 distribution. This is around 6.0. The units are microamps. This is about 13.8. The units are microamps. And those are 95% confidence limits for the process, or for the standard deviation of current requirement for any fixed set of conditions, that is, any fixed tube type. Okay.